We will be discussing the chemical process of coagulation. Coagulation is defined as a method to alter colloids so that they will be able to flocculate and form larger particles. It has been instituted in water treatment because direct sand filtration, which was first implemented, was found to be largely ineffective at removing bacteria, viruses, soil particles, and color. And recall that color is contributed mostly by natural organic matter. Realize that all of these are negatively charged substances. Colloids are suspended in solution and cannot be removed by sedimentation or filtration. Colloids are stable because they are extremely small and they are negatively charged, which causes them to repel each other upon collision. If you have two negatively charged molecules and they come into contact with each other, they will repel. If you have a negatively charged particle and a positively charged particle, these will, when they interact, they will stay together and have the potential to create a larger particle. This is the creation of what we refer to as a flock. Before a large flock forms, though, colloids are extremely small, and their movement is controlled by Brownian motion, which is defined as random movement. This is significant for engineers because we have no control over where these particles go. Once they get big enough, their movement will be controlled by gravity forces, and we can manipulate the velocity gradient of fluid to control movement. In order to destabilize colloids, they must be neutralized. So the general procedure is simply to add positively charged ions, and these are called coagulants, to the solution, and this neutralizes the charge of the colloids by causing that positive charge to interact with the negatively charged constituent to create a neutral particle. The chemicals we add, because coagulants are chemicals, these must be effective at neutralizing charge, non-toxic because we're adding them to our drinking water, and insoluble. And the purpose of this is so that the coagulants can be removed. One basic coagulant could be a salt of sodium chloride. When a salt is added to water, the cations and the anions are dissociated, so the cation, sodium +1, would be released into the solution. The higher the concentration of the salt, the lower the charge of particles in solution. If you think about what's happening in the reactor, you have negatively charged particles, which could be NAM or bacteria, and you are going to add sodium chloride, and it will dissociate. The sodium will be attracted, the positive charge of the sodium will be attracted to the negatively charged particles to neutralize those. The strength of the charge of a particle can be measured as the electric potential. And so you can imagine that when you are at the surface of a particle here, the charge of that particle is very strong. And so in a no-salt solution, the charge of that particle is high. And as you move away from the particle, the strength of that charge decreases. You can imagine this in terms of thinking of an electric fence. When you're touching the electric fence, you feel the charge very strongly. I do not recommend you do this. But if you were to touch the electric fence, you would feel the charge very strongly. But when you step back 5 feet from the electric fence, the strength of that charge is not as strong. So in a solution, when you're at the surface of a particle, the particle charge is very strong. And what this diagram tries to show you is if you increase the salt concentration, you essentially increase the positive ions that can interact with the negative. The strength of that charge decreases even at the surface of the particle. So the addition of coagulants neutralizes charge, and that is the definition of coagulation. Now, sodium chloride is not a typical coagulant that's used in water treatment because it would make our water salty. It is also fairly inefficient. I show you the figure I just showed of sodium chloride being added. And on this graph, I'm showing you the effect on particle charge against distance from the surface on the x-axis, and here would be a case of sodium. The valence of that sodium ion is +1. And you can see that it reduces the charge slightly, but if you add something that has a valence of +2, that charge decreases further. Finally, if you add something with a valence +3, you can see the difference between the efficiency. If our goal is to reduce charge, the valence +3 reduces it much better than a valence of +1. And so for this reason, we typically add trivalent cations as our coagulant. And the most common trivalent cations added are aluminum +3 and iron +3. Metal salts simply release their cations into solution. The ferric interacts with the negatively charged particles to create a metal precipitate, a flock. In order to determine the dose of how much coagulant should be added into a water, it really is impossible to predict that in a straight-up chemical reaction. And that is because we are not looking at a strict chemical reaction, we're looking at charge neutralization. So in order to determine the dose of coagulants that are used, water treatment plant operators typically perform something called a jar test. In a jar test, you simply start with 5 or 6 beakers of your source water, and you vary either the pH or you vary the dose. If you vary the pH, you set dose constant, and if you vary the dose, you set the pH constant. And by doing this, you can determine the optimal pH and the optimal dose for coagulation. pH is, of course, important because as you vary the pH, you vary the hydrogen ion concentration and the hydroxide ion concentration, and these molecules have charge in their own right. An image of the jar test is shown next. I'm showing you 2 different versions of jar test. In the first, this would be a typical jar test at a water treatment plant. The water is all fairly clean, as source waters tend to be, but as you look down the line, you can see that it becomes more clear. So clarity increases at this point. It's a little bit easier to see in this color photograph from my own laboratory where we were trying to coagulate algae. And what we were doing in this was varying the dose of a coagulant. And you can see here that the most clear supernatant, so you add the coagulant, you allow some flocculation to occur, and you see what settles. The clearest jar in this case was actually the middle jar. So if we were to graph this data from the algal jar test, I could graph turbidity on the y-axis in NTU and dose of coagulant in terms of milligrams per liter. And you would see that turbidity was fairly high in one of these, and then it dipped down and it came back up. The middle jar had the lowest turbidity at a certain point. And so if I were determining coagulant dose, I would predict that I would want to apply a dose between X and Y on this figure. There are 2 typical coagulants added: alum, which is the common name for aluminum sulfate, and I would like you to know the common name and the chemical name of alum. This is typically supplied as a liquid, around 51% by volume, and it has an optimal pH range typically between 5.5 and 6.5, but again, it depends on the source water. This compound is aluminum sulfate or alum, and this means that aluminum sulfate is combined in a hydrated form with 14 moles of water. When this is added and alkalinity is present, so alkalinity here is denoted by bicarbonate, a precipitate forms of aluminum hydroxide. Carbon dioxide is released and some sulfate. There's very little pH change with this reaction. However, when no alkalinity is present, alum dissociates and combines with water, which is not being shown here. Alum dissociates and forms that aluminum hydroxide precipitate, water, but in a troublesome fashion it also produces sulfuric acid. And if this happens, there is a significant pH drop in the solution. Ferric as a coagulant is very similar. Iron can either be added in the form of ferric sulfate or ferric chloride, and I'm showing you the example with ferric chloride. The optimal pH of ferric is typically between 4 and 9. It usually has a wider range of optimal performance than alum. Again, that would totally depend on your source water. So when alkalinity is present, alkalinity being shown here as bicarbonate, ferric chloride reacts with water and bicarbonate to produce the solid ferric hydroxide and then chloride ions and carbon dioxide. When alkalinity is not present, ferric chloride reacts with water to produce the solid and hydrochloric acid, and this also produces a pH drop. In addition to the chemical coagulant, there are 4 types of coagulant aids. Because coagulants have an optimal pH range, we typically would like to adjust the pH. Now, lime adjusts pH because it has hydroxide ions. Soda ash also raises the pH because it releases carbonate ion, which plays with the carbonate cycle. The next 3 are really going to optimize coagulation. Water treatment plants may purchase activated silica or clay. Both of these are negatively charged and can interact with the positive charge of coagulant precipitates to form larger, denser particles. These add significant weight and can aid sedimentation and separation. Clay has a benefit because it is also cheap as dirt. Are you laughing? The 4th coagulant aid is a polymer. Polymers are sort of made to order. They are synthetic typically, and these can be either negatively charged, positively charged, mixed charge. They're very effective at creating interparticle bridging to produce large flux, but they also are very expensive. These are typically added in very small quantities to just create a very efficient removal capacity. Okay, we're going to work an example now. Given an alum dose that presumably has been determined by jar testing, how much alkalinity needs to be present in order to prevent the pH drop? So I would give you the chemical reaction of alum or aluminum sulfate reacting with alkalinity, and you're asked to find how much of this needs to be present. So the general approach is going to be first to recognize the stoichiometric equivalent of alum to bicarbonate, which in this case is the alkalinity. The second step is going to be to calculate the molar concentration of alum. The third step is going to be to convert moles per liter of alum to moles per liter of alkalinity consumed using the stoichiometric equivalent in step 1. And the fourth step is going to be to convert the molar concentration of bicarbonate to the milligram per liter concentration of bicarbonate, and then to the milligram per liter concentration of calcium carbonate. So we start with 12 milligrams per liter of alum, and we know that alum has a molecular weight of 594 grams per mole. This gives us 2 times 10 to the negative 5 moles per liter of alum. And from reading the chemical reaction, we know that 6 moles of bicarbonate are consumed per mole of alum. And that leaves us with 1.2 times 10 to the negative 4 moles per liter of bicarbonate are required for that dose of alum. So 61 grams bicarbonate per mole gives us 0.007 grams bicarbonate per liter. And so 7 milligrams per liter bicarbonate can be converted to milligrams per liter calcium carbonate by multiplying by the equivalent weight of calcium carbonate and dividing by the equivalent weight of bicarbonate. 6 milligrams per liter calcium carbonate. So looking back, we started with a dose of alum, and we asked ourselves how much bicarbonate is consumed for that dose, which is the stoichiometric relationship, and then we converted to milligrams per liter calcium carbonate.